Welcome to the deep dive. If you are currently prepping for your ATPL theory exams, you know that mastery isn't just about memorizing facts, it's about locking in the fundamental physics that govern safe flight.
That's all right.
Our mission today is absolute clarity on the core system that defines an aircraft state, the Pitot and static pressure systems. We're going deep into the mechanics, the critical instrumentation they feed, and most importantly, the unavoidable errors that every airline pilot must understand.
That's a necessary focus, definitely. When we discuss performance, control, and ultimately safety, it all begins with the ability of the airframe to accurately perceive its environment. Success in this foundational area, especially in the context of advanced exams, hinges on clearly separating and defining three critical types of pressure and internalizing their mathematically precise relationship. This definition is the absolute bedrock for the airspeed indicator and the Machmeter.
Okay, let's unpack this then and lock in those core definitions right away. Because confusing these three pressures, well, it's the source of many conceptual errors later in the operational theory, isn't it?
It really is. We start with static pressure. Think of this as the normal ambient atmospheric pressure. It's what you would measure if the aircraft were just sitting still on the ground or, well, stationary in the air somehow.
Right.
It acts equally on the airframe from all directions, and its value is determined basically by altitude and temperature. It is, quite simply, the weight of the air column above the aircraft at that specific flight level.
So it's the pressure reference we use for altitude?
Got it.
Yeah. Now, when we introduce movement, things get interesting.
Precisely. The movement introduces dynamic pressure. Now, this is not the overall pressure. It is the additional pressure generated purely by the air's resistance to the aircraft moving through it.
Okay.
Think of it as the kinetic energy of the moving air being converted into pressure when it slams into the aircraft, so to speak.
Right.
The value of dynamic pressure depends entirely on the aircraft's speed through the air and the density of that air. And crucially, if you double your speed, the dynamic pressure doesn't just double, it quadruples. It's a squared relationship.
Which explains why speed management is exponentially more critical at high velocities. Makes sense. And that brings us to the combination of the two.
Yes, the combination is known as total pressure, or more commonly in aviation, pitot pressure. This is the pressure we measure right at the leading edges of the aircraft, or more specifically, inside the pitot tube where the airstream is forced to stop completely, to stagnate.
Okay.
In this specific location, you are summing the static pressure already present in the atmosphere, plus the dynamic pressure generated by the conversion of the air's kinetic energy into pressure.
And here is the crucial takeaway, the cornerstone of this system, especially for the exams. Instruments cannot measure dynamic pressure directly. They don't have a sensor that just isolates that movement component, do they?
No, they don't. Correct. The instrument system is physically incapable of isolating that component. Therefore, the system must measure total pressure via the pitot tube, measure static pressure via the static source, and then the instrument performs the necessary calculation.
Okay.
This relationship is non-negotiable and requires instant recall for you. Dynamic pressure equals pitot pressure minus static pressure. This simple subtraction is what allows the airspeed indicator and Machmeter to work, and understanding it is absolutely foundational. You'll see this again and again.
Right. Now that we have established the theoretical inputs, pitot and static, we need to examine the physical hardware responsible for collecting this data outside the aircraft. Let's delve into the design and placement requirements of the pitot and static heads.
Okay. The design of the pitot tube is functionally elegant, but aerodynamically demanding. It is basically an open-ended tube critically mounted parallel to the aircraft's longitudinal axis.
Wow, okay.
Yes. Its sole purpose is to capture the full energy of the moving air and bring it completely to rest inside the tube. Stagnation.
If the air is truly brought to rest, that maximizes the pressure measured, ensuring we capture the full dynamic component. I see the source material mentions the concept of a stagnation wall. Why is that significant? What does that actually do?
Good point. A stagnation wall.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.